you for having me. I would like to thank the organizers for having me. And thank you also for still being here at the end of this long day. I guess you all are tired, but I am a postdoctoral researcher at Imagine Institute in the Clinical Bioinformatics Lab that is led by Antonio Rossel. And today I'm going to present you COBT, which is a method that we developed during my PhD. So I guess that most of you all probably know that around roughly 70% of patients suffering from rare Mendelian diseases remain without a molecular diagnosis after their DNA sequencing. In rare diseases, we have few patients, and thus we lack statistical power. That's why we usually don't use methods such as GWAS for common diseases. We have developed in the past burden tests, which measure the accumulation of rare variants to compare between the cases and the controls. However, in practice, in rare diseases, we do not have matched controls, meaning we do not sequence controls at the same time as the cases, and we have to use external controls, which may lead to batch effects, meaning that what you may discover might be more related to technical artifacts than to biological factors. That's why we can use case-only methods to cope to avoid this problem. And so how can we cope with the absence of control? We may use neutral background variation that is observed in publicly available sequencing projects, such as NOMAD, which is one of the biggest publicly available databases to date. In version 2.1, there were already more than 100,000 available exomes. And this is what current methods, case-only methods, are doing. So TRAPT and COCO-RV are two methods that use NOMAD to infer the number of carriers expected in the sample from the general population. They will compare this to the number of carriers in their cases. So in the end, it's not per se a burden test because you compare the number of carriers regardless of the amount of variants inside your genes, meaning that if you have one individual that has one variant in one gene, it will count the same as one individual with 5 variants in the same gene.
Sorry, thanks, Rob. Just need to change one thing real quick here.
All right.
Okay, sorry.
No problem. Thank you. And so that's why we propose the method to fill this gap. So the basis behind our method is quite simple. Imagine that you have J number of individuals and I number of genes with N rare variants scattered among the genes of those individuals. This can be modeled as a multinomial distribution. Now, if you sum all the variants across your individuals for one gene, this becomes a binomial distribution that can be approximated by a Poisson distribution. And the rationale behind our test is to identify genes that display an accumulation of rare variants that is higher than expected by chance. Now, how do you have this higher than expected by chance? We apply, as I said, a Poisson test with a Poisson distribution. And we have a probability of mutation that comes from your publicly available cohort, so NOMAD in our case. We applied our strategy on 2 different data sets with 2 different aims. The first, we wanted to characterize the behavior of our test. So we wanted a negative control with healthy or supposedly healthy individuals. That's why we focused on non-Finnish European individuals from the 1,000 Genomes Project. And we used synonymous variants, which are supposedly neutral, because it's a negative control test. So we do not expect to have any enrichment of synonymous rare variants. We applied some goodness of fit tests to see if the Poisson distribution was appropriate for our test. And as you may see here in this table, less than 0.5% of our genes were rejecting the test. So we assumed that the Poisson distribution was appropriate for our test. Now, what you can see here are 3 quantile plots for, on the left, our test, and on the right, the 2 tests I mentioned earlier, TRAPT and COCO-RV, which are the case-only tests. So two things to notice. If you take a look at the y-axis of those quantile plots, you will see that for COBT it's lower than for the two other tests, which means that we have detected less genes enriched in rare synonymous variants, so we are less prone to type 1 error, so false positives. Also, there are two lines on each of those plots, a red line, which is the bisector, and a blue line, which is this lambda delta 95. It's a measure of the genomic inflation. So the closer it is to the red line, the better. And this is also the slope that you can see on each of those three QQ plots. And the closer to 1, the better, again, which means that COBT has a better control for genomic inflation and a better control for false positives than the two other methods. Still, we have identified, even though we have a low rate of false positives, we have identified 9 genes that were enriched in synonymous variants, which was unexpected. I won't have time to explain further here, but we think they may originate from general population stochastic random sampling, and that they can also partially be explained by population structure biases. I can explain further maybe later if you want, or you can also check the preprint that I will show at the end for more information about that. So basically, the test is valid statistically, and we have tested it on real sequencing data, but we wanted also to see how it was, what was the behavior of it with the disease cohort, an actual disease cohort. So we focused on ciliopathy patients, and this time we focused on protein altering variants, which are potentially harmful variants, because now it's a clinical application. So we focused on ciliopathies because it's a rare disease family that affects the cell cilia, and it has a high genetic heterogeneity and a high phenotypic heterogeneity. So it's a very good use case for our test because it's hard to analyze. We applied COBT, and we detected 15 genes that were enriched in protein altering variants. We had 194 patients with variants inside those 15 genes among our cohort, and out of them, we knew the causal gene for only 82 patients. Among those 82 patients, we had recovered the causal gene for 21. So we wondered, is it more than expected by chance? Or well, is it good, is it bad, basically? So to measure that, we run Monte Carlo simulation, meaning that we randomly selected 15 genes and checked if by chance we would recover the causal genes of the patient. We did that 1,000 times, and we compared it to the true value. And this is what you see on the left. So with the red dot being the true value, 21. And so as you can see, it's more than expected by chance. So which means that COBT can indeed identify causal genes in a real clinical setting. And then what about the remaining patients, the one for which we didn't know the causal gene? For 56 patients, we have found potentially harmful variants in the 15 genes that we identified. So we asked clinical experts at the institute to go back to their clinical records and to check if the clinical signs of the patients were compatible with the genes we have detected. And for 19 patients, it was the case, meaning that COBT may also reveal potential new associations. So to conclude, the take-home messages about these presentations are that COBT is a Poisson-based per gene burden test that is used in case-only settings. And we use observed aggregated frequencies that come from reference cohorts, such as NOMAD. It's valid regarding its statistical assumptions, and it's capable of controlling for false positive rates, as well as genomic inflation on real sequencing data. And we have also seen that it can recover already known gene to phenotype associations, as well as propose novel candidate genes in a clinical setting. The limitations of the method are that as compared to classical burden tests, you cannot integrate covariate here. I did not have time to explain, but it's sensitive to stochastic sampling and to maybe some cryptic genetic background biases. And as for other comparable types of methods, it's also limited by low cohort sizes, which is kind of expected. So I would like to thank all the people that were involved in this project, and to thank you also all for your attention. The method is now available on GitHub if you want to check. And also we have just released a preprint, so you can scan the QR code if you want to access this. So thank you all for your attention.
Questions?
Thanks, that was very interesting. So you said at the end there that you're sort of susceptible to stochasticity when you've got small sample sizes. So is that in terms of the number of patients or the number of mutations in a given gene?
When I said that, it was related actually to when we tested when we tested the strategy. So here on the 1,000 Genomes project. So it's not a problem of number of individuals. Actually, it's more a problem of the comparison. Well, it is actually, yes. See, it is a problem of the number of individuals. I can actually show you. I have a plot. Indeed, what we did here, it's the same plot as before, but with a random sampling, meaning that for 1,000 times, we sampled half of the data set, and we applied the strategy again. And then with the same plot as before, we have colored the dots with the number of times they were significant. So the first thing that you may see is that it's the same genes that are significant, which is reassuring. But it also means that it depends whether we were having the right individuals in the sample or not. And so it means that we have a fraction of those gene hits that originate from stochastic sampling. So it is indeed related to the number of individuals, but also to the number of variants, because if you don't have those individuals, you have 0 variants and you will detect nothing. So it's a matter of sensitivity in the end.
Thank you. That was a nice talk. It's kind of building on the previous question. I was wondering, you took the 1,000 genomes, but I was wondering if, like, you're going over time, if there's more data, you're going to like consider from different backgrounds, like African genomes, and like, is that diversity, like genetic diversity, taken into account?
Diversity is not taken into account because we cannot have covariates, but it's a very good question, because in the end it has a high impact, and actually here on top of that we wondered if it had an impact, and we have checked it. Here it's a PCA that was done on the common variants, and we have seen that the 9 genes that were enriched in synonymous variants, 3 out of them were actually associated with one of the subpopulations from Europe. So for sure, if you have discrepancies between your data and the database you are using, so for us it was Nomad, you will have differences in the end. You will maybe have genes that will pop up within the test that are linked to the discrepancies between the populations and not to a true disease-related problem.
So to follow up, how are you going to like compensate for all these variations? Because this means that your tool, you have to apply it to, or the user will have to consider geographical considerations depending on the data set.
It's a good question. Actually, I would advise people to check that afterwards, basically. As you cannot, because of the way the test is built, you cannot integrate that. So I would just advise people to test afterwards if it makes sense or not, and ask clinicians, of course, to check if what you will have in the end makes sense. And if it does not make sense, maybe it's related to, for example, geographical data. I hope it answers your question.
Hey, thanks a lot. Oh, it's on. Yeah. So it's the ancestry thing is one challenge, but one other thing I wondered about is so you get all these technical biases between data sets. Some kinds of variants are less reliably genotyped than others, you know, indels, for instance. I was wondering if you'd considered taking just maybe some random control data sets and comparing them to Nomad in this kind of way to see if you sort of can like come up with any features to kind of show this false positive rate is well controlled across, you know, different kinds of exome sequencing data sets or something like this.
I'm not sure I'm understanding your question.
So the idea is different data sets might have different features. Maybe it's exome sequencing or depth of coverage, or you're including indels or you're not. And I wonder if you'd considered maybe just taking some control cohorts that are out there and seeing if some of these maybe give you fake associations that you can maybe provide some more guidance on when this is more or less reliable.
I see. We did not directly consider that, but we are aware that you can have a lot of other problems. For example, as you said, the coverage. For coverage, we do already take that into account. Basically, when we test the genes, we do not test the whole gene. We want to have only a fraction of the gene for which it is sequenced at 10x in at least 90% of the cohorts, and also a median coverage of 10x in Nomad. Then this means that we are supposed to have something that is comparable between Nomad and the cases that we test. But as for the other things that you mentioned, no, we did not really test for that.
All right, let's thanks Antoine again.